Hey everyone, welcome to the third video for section 3.8. So in this video we're looking at the forced and undamped oscillator. So we're going to take away the damping from last time, and we're going to see what sort of stuff can come out of this. So in particular, in this case, you can get different sort of phenomena that show up, namely beats or amplitude modulation, which will show how those sort of work. And then you can also get resonance, but in this case you don't get resonance in the physical sense as before. You get fully uncontrolled resonance that goes off to infinity as time goes on. So we'll talk about all those. We'll see how all those work, and then sort of work all that together. All right, let's jump on into it. So we're looking at the undamped forced oscillator in this case, which means we have our ODE is of the form mu double prime plus Ku equals F0 cosine of omega t. And our natural frequency, omega 0, is the square root of K over M. Now, comparison to the last one, this one's fairly easy to solve out explicitly. We can solve this out pretty easily explicitly because we can just we know our general solution here is just C1 cosine of omega 0 t plus C2 sine of omega 0 t. That's our general solution for the homogeneous case, plus some constant times cosine omega t plus b sine omega t coming from undetermined coefficients. And this is assuming omega is not omega 0. If it is, you have to put t's in front of those guys, and that t is what gives you the unbounded resonance as time goes on. So we're going to come back to that case later. But for now, we'll assume that omega is not omega 0, so we're not at the natural frequency. And then we can solve this out for a and b. And it turns out, if you want to solve this, you end up with a general solution. U of t is going to be C1 cosine of omega 0 t plus C2 sine of omega 0 t plus F0 over M omega 0 squared minus omega squared cosine of omega t. This ends up being your solution here. It's just something like that. Now, an interesting case to look at is what if we start at 0, 0? So we start with the spring, just the mass in the center of the spring where it would normally sit, and we don't force it, we don't bump it at all to start it, we just start the force and see what happens. So if we want u of 0 equals u prime of 0 equals 0, so we're just going to start by leaving it there and turning on the force. This becomes u of t equals f0 over the same constant times cosine of omega t minus cosine of omega 0 t. So the sine term vanishes from that as well. So that's interesting. It looks like a difference of two different cosine waves, which is one way to look at it. But you can also use some sum and difference formulas for cosine to rewrite this a little bit differently. And I can rewrite this in this form. 2 f0 over that same denominator times the sine of omega 0 minus omega over 2t times the sine of omega 0 plus omega over 2t. So I can rewrite this difference of cosine functions into a product of sine functions, which is sort of strange at first, but it could give us a little bit of intuition as to what's going on. Now, if omega 0 is close to omega, then this term here, this first term here, oscillates very slowly. Especially it oscillates slowly compared to the sum of omega 0 and omega. So we can think of this as a sine wave. The sine wave sine of omega 0 plus omega over 2t with varying amplitude 2f0 over that bottom, this in absolute values. So it's a sine wave of a high frequency whose amplitude sort of varies slowly in a sine wave curve. And this sort of feature is what we call beats or amplitude modulation. And we only see this sort of thing in the undamped system because it's going to be periodic that goes off to infinity. The one part isn't just going to die out because it went to 0. Since nothing here dies out, they interact together forever off to infinity. So that is one thing that can happen, and that's the main sort of feature that pops out of these sorts of equations. As you'll see when I draw some pictures, sometimes it's better to think of it in the form of a difference of two cosine waves, and sometimes it's better to think of it in this sort of product form down here. And I'll show you some pictures to sort of show you how that sort of comes together. Now, the other thing that can happen that we haven't dealt with yet is what happens if omega equals omega 0. Then the general solution is C1 cosine plus C2 sine plus AT cosine plus BT sine. And in all likelihood, well, really, if you set it up right, this A and this B will not both be 0, which means I get a solution that is unbounded as t goes to infinity. It just keeps growing, growing, bigger and bigger and bigger as time goes on. And this is what resonance looks like in these systems. Since there's no way to lose energy at all, it just keeps building and building and building energy and going further and further away and just goes off to infinity. All right, let's look at some pictures of this and see how it works. All right, so here we have an undamped system. I've just picked K to be 4, which means my omega naught should be 2. So here I've picked omega to be 1.9, which is fairly close to omega 0. And if I solve the equation the same way, this is the graph that I get. As you can see, this is definitely the beat phenomenon here that we're talking about, where it sort of beats in different ways as time goes on. It's a fast oscillating sine wave with amplitude varying in a slow manner, so you get these beats. Which the same thing that you hear with sound waves when you hear if people are singing off pitch, you hear little beats in there. If something's a little bit out of tune, you'll hear beats. This is what you're hearing, something like this. So now let's see what happens if I take this and I make my omega get closer and closer and closer to 2, because 2 is where my omega 0 is. So let's say 0.95, what happens? The whole thing is sort of drawn out more. It's drawn out a little bit more. The beats are longer than they were before. Let's keep changing. We get to 1.99, now we're just growing. It's just growing faster and faster, bigger and bigger and bigger time. So yes, since these two are not equal, it will come back down eventually, but it's going to take a long time before it gets there. And now if I just put in omega equals 2, I get very straight, very well-defined resonance where it's just growing at the rate of t, just getting bigger and bigger as time goes on. Now I mentioned about when it might be more easily to view it as a sort of different form. We're looking at it as the difference of cosines versus the product of the oscillation stuff. Let's make omega huge, so say 10. Now this graph looks a little strange, but it might be possible to see that you've got sort of an inner sine wave going on, and as you follow it out, you're tracing out the other function you want. You're tracing out, you have a bigger sine wave sort of oscillating on top of a smaller one. Let's even make it bigger if we can make that any clearer. Yeah, that's what I was going for. So this one you can sort of see as you're adding two sine waves together. You got the inner cosine wave that makes it go up, down, up, down, up, down, and then you've got the faster one sort of going on top of it, oscillating up and down to give you the sort of pattern when you're done. So in this case, it's helpful to view it as a difference of two cosine waves, whereas in the other case, it was usually developed as a multiplication because you wanted to see that you had the combined, so the slow oscillation combined with the faster one. All right, so there's the points for this video. In the next one, we're going to look at a couple examples of problems you could solve using this sort of method, and I will probably again be using Maple to solve those problems just because the algebra gets kind of nasty when you want to show multiple things at once. That's it for this one. Resonance, beats, important stuff for undamped system as well as the resonance for the damped system which we talked about last video. All right, thanks for watching, and I'll see you in the next one.